Very organized.
All right. Quick recap from last week. As Julia pointed out, the last video I recorded sounded like something out of The Exorcist or something.
Yeah.
So anyway, if you tried to watch that, just watch it on mute maybe. Here's the recap. Hopefully the audio is not gross this time. So let's do I don't know. We could skip down to the 6, I guess. It's a really steep ramp. 60 degrees. So what happens here is the trick is you make this your x-axis, and you make this your y-axis. Okay, so your x-axis runs parallel to the ramp, and your y-axis runs perpendicular to the ramp. And then so what that allows you to do is look at this vector. So in this problem, it's a 25 kilogram block. So how big is this vector here? Gravity of it. 25 times 9.8, so is that 245? Is that right? Someone confirm for me. 245. Okay. All right, so gravity is pulling down at 245. So what makes this interesting is a lot of times gravity just points along the y-axis, but since we determined or we picked this weird set of axes, now this vector is like at an angle and you can decompose it into its components. And so this vector is going to have a component that's perpendicular to the ramp, and it has a component that's parallel to the ramp. Okay, so I have a little box here. Does this box idea make sense to everyone, or is it like just like confusing? This is a rectangle. So, and then remember this angle would also be 60 degrees, right there. Is everyone okay with the geometry of that? How like this would be 30? Because I can imagine a right triangle here, like a smaller right triangle. Yeah. And so 60, 90, 30, making this 60, because that's a perpendicular right there. So, and that's generally true. There's nothing special about the number 60. If this had been 52 degrees, this would be 52 degrees. So it's very handy, because then what you can do now is basically maybe imagine turning your head totally almost upside down and observing this triangle. So this triangle here has a hypotenuse. And so this adjacent side, this dashed vector here, this would be 245 times the cosine of 60. And this long vector here, that's basically the opposite side on that triangle. Let me just draw the triangle again here, just to make it as clear as I possibly can. That's the triangle I'm looking at. So that's 60. This is 245. This is a right angle. Does that make better sense, maybe? Those two triangles? Okay, so then this is the adjacent side. This is the opposite. And this is the hypotenuse. So the adjacent side is 245 times the cosine of 60. The opposite side is 245 times the sine of 60. And so the calculator, you can get, this one, you don't really need a calculator for it. It's 112.5. Because I know this cosine of 60 is 1/2. This one would be, what do we get here? 245. Make sure you're in degree mode. Here you get 212.2. All right, do we feel okay about that?
It's raw. I plugged a 245 into 60. 120.
Just testing you, Winslow. Lamau. Because half of 240 isn't 110, is it? Facts and logic. Thanks, Winslow. After I was like, oh, you don't need a calculator for that. Just divide it by 2. And do the division wrong. Okay, so we're okay with that, right? So this is now the thing about this axis choice that's really nice is I know that in the y direction, these have to cancel out because if the y direction vectors didn't cancel out, then the block would have to accelerate either off the ramp or somehow into the ramp. So that's not happening, obviously. So this vector here, by the way, what is that? Like what actually is that force? It's the normal force from the ramp. So the ramp is made of some solid material, wood or something, and that wood exerts a force on the block that prevents the block from just plummeting straight down, right? So the normal force then would be how big? Very good. It would be just as big as this vector here. So 100. Okay. And so what is the net? So we got the normal force. We're done with that. So the normal force is this. 122.5. It's not asking for the net force, but we have to get the net force to find the acceleration. So we have to go F net equals MA. All right. For $1 billion zillion. Who can tell me what is the net force on the block? What? Very good. Very good. Big brain indeed. The mass is 25. Yeah, let's go back a second. This is a pretty complicated diagram, so it's not obvious why the net force is that, but does it make sense why? So like there's really only 2 vectors here. There's the gravity and there's the normal force.
Yes.
Now the gravity, his y-axis component gets canceled out fully by the normal force. So all that's left over is his x-axis component. So that must be the net force. Okay. So the net force is that size and it points just along the ramp. Everyone okay with that? Mm-hmm. Okay. Now look what we get for the acceleration. It's a big number. I know it's 8 point something. Mm-hmm. Anyone got the? Someone give me the rest of this.
8.48.
8.48.
Yeah.
What do you notice about that number? You know the word for that? It's pretty dang close to what? Yeah, it's pretty close to 9.8. So, and that shouldn't surprise you too much. I mean, a 60-degree ramp is pretty extreme. You would be accelerating pretty fast. So. Yeah, it's, yeah. Elevator?
Right? Chair 1, the drop.
I don't know what you're talking about, but
Never heard of elevator.
for skiing, that's pretty extreme. I think you're talking like pro level, like super extreme terrain, I think. Even 45 degrees, you get on a 45-degree slope. Doesn't seem like that'd be that steep, but that's pretty steep. That's way too steep for like most intermediate. skiers, I think.
Yeah.
No, I was just saying generally, like it always seems steeper than it really is. There's a lot of slopes where I think I'd be like, oh, this seems like 45 degrees, and it's actually like 25 degrees. It just seems it's like an illusion of steepness. Okay, so do we feel okay with this process? So let's summarize on number 7. Let's summarize the result. So on number 7, it's the same process, but we're just going to basically generalize this and get a formula. So quick little diagram. Here's the block. All right, so what's the downward force? If this block is just M, this is going to be mg. And then so our components. So there's my components. There's my y-axis. There's my x-axis. How big is the y-axis one? Yeah, mg times the cos. So remember, this is theta. So that theta would also show up in that little triangle right there. So this adjacent side is mg cosine theta. This opposite side on the triangle is mg sine of theta. Not to be confused here, that's the x-axis component. So what is our formula then for the normal force? Mg cosine theta, very good. So this is one we're going to use a lot. I hope you've understood why this works, but from now on, we're pretty much just going to like say, this is something we know. Because it would take, it would definitely reinforce understanding if we derived it every single time, but that would just take a long time. So if you're feeling that you don't really understand any of this stuff, try to address that now. I can discuss it with you if you're still confused, but hopefully you get the why here. Why is this? Okay, so then when I go to find the acceleration, I go F net. Here's another thing that really is important. Okay. Does the net force depend on the mass? Yes. Because by the way, what is the net force?
It's going to be the mg sine theta.
Very good. Mg sine theta. Now, a follow-up question. Does the acceleration depend on the mass? No, it does not. So a 1 kilogram block versus a 5 kilogram block, they would have the exact same acceleration. And here is our nice relationship for the acceleration. It's just, that's very elegant, very, very simple. What's the acceleration? Well, it's just g, gravity, 9.8, but you have to multiply it by the sine of the angle. So what happens when theta is 0? Acceleration is 0, right? Would you do that mathematically? Like, well, I know the sine of 0 is 0, so I'd get 0. Or to think more common sense wise, if theta was 0, it'd be a flat. And then likewise, let's say theta was 90 degrees. If theta was 90, it'd be a vertical ramp. Kind of see, there's your cliff, right? That's an actual cliff. If theta is 90, what's the sine of 90? 1. Oh. So if theta was 90, I'd have g times 1. So that makes sense too. Makes sense too, right? All right. One more thing to point out, guys, is if this was a person, I know a 25 kilogram person, I guess it could be a child. This person, when they step on their scale at home, back to the probably did before, this is what the bathroom scale reads if they have some weird Newton scale, right? But what did their scale read while they were, say, skiing down this thing? This. So they feel, they're subjectively speaking, they'd say, I feel half of my weight, right? Makes sense? Because this number is half as big as that number.
Well, because it's
Their products.
I was gonna say something, it's hard to describe, but like, at first I was thinking it was like the.
Like, common sense wise, it makes sense, but why?
Well, we got the number using the trig, right? And what I'm saying is, what makes you feel your sensation of weight? Not really, because if you're free falling, right, you don't feel any weight. So what really is making you feel that sensation of weight is the normal force. So like back to this thought experiment where let's put you in an elevator. Here, let's put you in an elevator out in deep outer space. You're way out in deep outer space. And then we just put a little rocket on here that accelerates you at 9.8 meters per second squared. Are you going to know any different? No, you're going to think, because what's going to happen is there's going to be a force exerted on you. The force is going to be your mass times your acceleration. And you'd say, okay, I feel my normal weight. So yes, Colin is spot on there. What makes you feel your sensation of weight is really that comes from the normal force. So if you think back to those elevator problems, these ones where like, let's say we're moving up and then we're going to accelerate. We're going to start going faster. So suppose that your weight is, just keep it simple. Let's say you're a 1,000 Newton person. Your weight is 1,000 Newtons. But let's say in order to accelerate, the elevator pushes on you with 1,500 Newtons. How does that make you feel? Well, you'd say, well, I'm accustomed to when I'm just standing at my house, how much force does the floor exert on me? 1,000 Newtons. But right now I'm feeling 50% more than that. So I'd say I feel about 50% heavier than I usually feel. So the same thing here, I'd say, well, I'm accustomed to feeling 245 Newtons of normal force, but during this event, I feel only 122.5, which is half as big. So that person would feel half as heavy as they usually feel. All right. Some kind of trick questions now. Not really trick questions. They're more like, do we understand what the heck is going on? Who feels brave? The answer number 8. If you have a 6 kilogram block and a 14 kilogram block at the top of a frictionless incline of 38 degrees, and you release them at the same time, which one will reach the bottom first? Don't shout it out if you know it. Think about it. Obviously, we have to do some intense calculations here. Okay, I think I have the answer. All right, I got the answer. Who thinks they know the answer? Julia. Huh?
Like they reached it at the same time.
Very good. So they're going to hit the bottom at the same time. What's a good explanation for that? Why?
Mass is not in the equation, so it won't make a difference.
Very good. So assuming they have the same starting velocity, assuming there's no funny business where one of them gets a head start or gets a little boost at the beginning, they're going to have the same exact acceleration because the mass isn't in there. And so if they have the same theta value, then they'll have the same acceleration, and thus the kinematics will be the same. So they're just going to reach the bottom at the same time. Okay, great. Nice job. How about number 9 says you have 2 10 kilogram blocks. One is on a 30-degree frictionless incline, and the other is on a 45-degree frictionless incline. Which will experience a greater acceleration? This one I think is maybe a bit easier. Maybe not. Depends if you have an intuition for how the angles behave, how their sines behave. Winslow, what do you think the answer is? It's the 45. It's steeper. Yeah, maybe that's a simpler way. Yeah, it's steeper. So just to clarify, so in case anyone was like, well, is there anything tricky going on with these sines? Like, because you might have looked at this and gone, well, who has a bigger sine value, 45 or 30? Well, it's 45. And if you graph theta versus the sine of theta, right? Say between 0 and 90 degrees. Can anyone visualize this? Do you see it in your head? How about two endpoints? When theta is 0, what's the sine of 0? 0. How about 90? What's the sine of 90? Okay. Who wants to be a millionaire? Does the curve go straight? Curve like that, or do something crazy? No! Oh my goodness. No, it's like this. Because the whole graph would look, I mean, you guys have seen this graph.
Oh, yeah.
That's the sine graph. I'm just slicing out this tiny little piece of it. I just lost a million. I saw a video today of apparently this guy in England cheated on Who Wants to Be a Millionaire, and his system was so stupid and obvious. Like, he's literally sitting in the chair and he would go, well, I'm wondering if the answer is A, but maybe not. Maybe it's answer B. And then from the audience, and like, so his system was someone in the audience, I guess he had some like smart person in there or someone with a phone, they would cough loudly when he was like pondering the correct answer. And it's funny, he gets all the way to like the $1 million question. And by that point, I think the host is like, has figured it out. And the host is kind of like, just, I don't know, asking these passive aggressive questions. Like, well, you just said you thought the answer was D and now you think it's C. Like, anyway, I just thought it was great. Maybe you can find it at the end of class. It's pretty entertaining. Okay, so anyway, I like the answer for 9 of just, 45 is steeper. It's going to have better acceleration. But yes, you can also connect it back to the formula and say the sine of 45 is greater than the sine of 30. One of your quiz questions is going to be something like, it'll be something like this, just a heads up. It'll say, hey, here's a 30-degree incline. Here's a 45-degree incline. And it'll say, if this guy has an acceleration of A, what is this guy's acceleration? It'll be one of those style questions. And so the way you might do that is you might say, well, this guy, his acceleration is g times the sine of 30, which the sine of 30 is 1/2. And this guy, call it question mark, I guess. His acceleration is g times the sine of 45, which is root 2 over 2. And then you'd figure out what is the difference. Well, this one is this guy times the square root of 2. Does that make sense? Through a substitution. So you'd say, okay, this guy is bigger than this guy by a factor of root 2, which is about 41% larger. Because root 2 is 1.41, roughly. Okay, number 10. This one would definitely stump most people, like if you did like a survey on the street. If you said, you got a 7-kilogram block on a 20-degree incline and a 59-degree block on an 18-degree incline, all frictionless, which one will accelerate faster?
The 7. Yep.
Yes, very good, the 7. Because the mass, yes, we can be really fancy, say, oh, it's invariant to the mass. Hit with some of these, right? So yeah, so the key here is don't let the 59 and the 7 fool you. You can see why most people might go, well, the 59 is heavier. They might think that the heavier block's going to go faster, but it's not the case. So yeah, so that one, the 7-kilogram block, because 20 degrees has a bigger sine value. Okay, and then for 11, I would like to cover the friction at the end of class today. That'd be a good place to stop. So I think you guys probably get this, right? I mean, hopefully you understand those basics here. 11, you're gonna have to use a little bit of kinematics. Is that clear enough? You're gonna have to use that 1/2 AT squared plus V naught T formula to figure out how fast it actually goes. All right, and then there's a couple more questions. I imagine we might need to seek some clarification on maybe 14 and 15 but try them, try to figure them out. Last thing today, guys. What if we throw friction in here? Is this going to greatly complicate things? No. Very good. Good answer. The answer is no. It's actually pretty simple. The hardest part really is just the same thing that was difficult before, which is keeping straight the whole static kinetic thing. So you recall, like, there's a certain amount of static friction that can be generated between the block and the ramp. And in order for it to move, you have to surpass that threshold. And then once you pass that threshold, it starts moving, then you look at the kinetic coefficient. Okay, let's get into it here. So we've got 10 kilogram block on a 25-degree incline. 10 kilograms. And then the static friction coefficient is 0.39. Okay, so what is going to be let's just jump straight to the value here. What is this component? Very good. Very good. 98 times the sine of 25. Is everyone okay with that? Does that make sense? So let's get a number there. That is a decimal. That's 41.4. Great. Newtons. Okay, so that's, you can think of that as being kind of like, and I stress the word kind of like, how much is gravity, how much of the gravity vector is pushing this thing down the ramp? Technically, it's gravity and the normal force kind of working together in a way. But anyway, so that's the component of gravity down the ramp. So, okay, and then how about this vector here? Don't forget, the actual vector is, there's the 98, but I don't really need that one so much. How big is this vector though? Very good. So again, you just go mg cosine of theta for this one, mg sine of theta for the parallel to the ramp, mg cosine theta for perpendicular to the ramp. Mr. Quackulator, 98 cosine of 25, 88.8. Okay. So how big is the normal force? Very good. Okay, here's the fun part. How much friction force can this system generate? Static friction. What were you going to say, Winslow? You're going to multiply.
You do mu times the normal force.
Very good. So 0.39 multiplied by what's the normal force? 88.8. Okay.
And that gets you 34.62.
Okay. So let's think about this. according to our static friction formula, whatever these materials happen to be made of, there's the static friction can be anything up to this amount. By the way, would that change? Would this number change if you tilted the ramp? If you changed theta?
Yes.
Yeah, because this number depends on theta. So if you change theta, you change this, which changes this. So it's actually a pretty complicated scenario here. So as you tilt the ramp, you actually decrease the normal force and you decrease the amount of friction you're capable of providing. But anyway, is it fairly obvious that it's going to slide on the ramp now?
Yeah.
Because there's more gravity pulling it down the ramp than there is friction to prevent it from sliding. So a longer problem of this type would then continue and say, hey, here's also the kinetic coefficient. You calculate that, get the normal force, or try to get the net force, and then get the acceleration. So we're out of time, but so 17, you can try that one out. And let's say I would like you to try 18 on your own, because if you can solve it, there's a very interesting answer to this question, which is if I've got an adjustable ramp and I just slowly increase it and increase it and increase it, and then the block first starts to slide when we hit, say, 37 degrees, is that enough information to get the coefficient of static friction? And you end up here, you get a very, very cool answer for 18 if you can solve it. So anyway, give it a shot if you can find the time tonight. And then we'll go over it tomorrow. Okay, wait, hold on. I'm going to keep it going for Caleb's joke. All right, Caleb, answer the joke.
So, Blue Skywalker walked through the kitchen, right? And there were two glass containers sitting next to two sinks. What did he say?
Look at those two glass containers.
He said, haha, it's Jar Jar sinks.
Yeah, that's, even for you, that's pretty bad.